So for the homework 3.3 through 3.5, let's take a look at an example or two. Here we have a problem where we have a mass that is being released from a height. It's being released from rest, and it's allowed to fall under the influence of gravity. So here we have an object. It's falling. When time equals 0, it's 3,000 meters above the ground. The object is 10 kilograms. What do we know about an object that's falling? When it's falling, we know that its weight is pulling it downward. But if we include air resistance, we know that air resistance is resisting it. So air resistance is proportional to the speed it's going. The faster it's going, the more air resistance there is. The slower it's going, the less air resistance. So BV can represent the force exerted by air. So the force is proportional, B is the proportionality constant, to velocity. Now they give us that B is 50 newtons second per meter. Notice if you multiply that times a velocity, which is going to be meters per second, the meters and the seconds would cancel, and that would leave you newtons, which is a force. Also, they tell us to use 9.81 meters per second squared for gravity. And they say let x of t represents the distance the object has fallen. Now, if x of t is going to represent the distance it's falling, we have to be conscious of what does that mean. So often we would set a coordinate system up where the height at the ground is 0, the height where it is released is 3,000 meters. But that would actually be backwards if x of t represents the distance it has fallen. We don't want at time 0 x to be 3,000. We want at time 0 x to be 0 to represent that when we start the clock, it hasn't fallen any. And then when it gets to the ground, it's fallen 3,000 meters. So we can set our coordinate system up however we choose. Based on the question here, this is the way they want it to be set up. So that means that we would consider downward a positive direction. Often in physics, we set things up where up is positive and we measure things from the ground. Here we're measuring from where we released, and we're considering down to be positive. So what else do we say? We say we were releasing it from rest. So our velocity at the beginning is 0 meters per second. So if we sum our forces, the sum of our forces should equal MA. Since it's going downward, it's accelerating as it's going downward, so our acceleration is a positive acceleration. So we replace mass with 10, and our acceleration is positive. On the other side, when we sum our forces, if down is positive, mg is a positive force. bv is an opposite of that direction, so that's a negative force. M in our case we said is 10, G is 9.81, B is 50, and velocity is changing, and acceleration at a given moment could vary. So if we multiply 10 times 9.81, we get 98.1 minus 50V equals 10A. Now we're wanting to find x of t. We want to find what is our position as a function of time. Well, if we take the derivative of velocity, it gives us position. but position is the second derivative of acceleration. We don't want to write this as a second order differential equation because we haven't gotten into solving second order differential equations yet. So then how do we handle that? Well, acceleration is the derivative of velocity. So we could change A to dv over dt. So we could solve our differential equation in terms of velocity. And then once we get velocity, if the derivative of velocity is acceleration, then the integral of velocity is position. So solve the differential equation to get velocity as a function of time, and then we can integrate that with respect to time, and that'll give us our position function. Remember from Calc 1 that velocity is the derivative of position. Velocity is the rate at which position is changing. Acceleration is the derivative of velocity. It's the rate at which velocity is changing. So if we work backwards, if we have acceleration, we integrate it to get velocity, integrate velocity to get position. So we need to solve our differential equation. So let me rewrite this. So we've got some room. Let's call this 10 dv dt equals 98.1 minus 50v. Let's divide both sides by 10. So we get dv dt by itself. So that gives us dv over dt. If we divide both of those terms by 10, we would get 9.81 minus 5v. And this is separable. This whole right side is a function of just one variable. It's not one factor that has v and t both in them. So remember, if we can isolate dv dt or dy dx or whatever on one side, and we can write the other side as a function of one variable times a function of the other variable, then it's separable. Well, we don't even have any t's on the right, so we could consider that function just a constant. So yes, this is going to be separable. So we could multiply both sides by dt to get t on the right, and then we can divide by the parentheses to get our v's on the left. So those cancel, so we're left with dt, or we could call that 1 dt on the right, on the left dv over 9.81 minus 5v. And then we can integrate both sides. So on the right side, when we integrate a constant, we pick up our variable plus c. If the left side is going to be du over u, for that to be u, then du would be negative 5 dv. So we would need to pick up a negative 5 on top, a negative 5 on bottom. So now the top is just the derivative of the bottom. So that's going to leave us negative 1/5 out front. And when we integrate du over u, that's natural log absolute value of u. And now we just need to solve this for v. To get rid of the negative 1/5, we can either divide by negative 1/5 or we can multiply by the reciprocal. So that the negatives cancel, the 5's cancel, that leaves us natural log. When we do the right side, we're going to have negative 5 times t. And when we multiply a constant times another constant, that's just going to be a constant. To get natural log, we're going to do e to both sides. So e and natural log cancel, and that's going to give us 9.81 minus 5v. On the right side, that's going to be e to the negative 5t plus c, or we can say times e to the c, which a constant raised to a constant, that's going to be a constant. And now we just solve this for v. We can subtract 9.81 from both sides. So c e to the negative 5t minus 9.81. Then we can divide both sides by negative 5. And this will give us a v. So when we do the first term divided by negative 5, we have a constant divided by a constant, which is just a constant, e to the negative 5t. And then when we do the second term, negative divided by negative is positive. And if we do 9.81 divided by 5, we get 1.962. So that's our velocity function, but we need to find c. We need to find c. So what do we know? We know that when time is 0 seconds, our velocity at that time is 0, because we're dropping it from rest. We're dropping it from rest. So that means if we substitute a 0 in, then our answer should be 0. At this time, this is our velocity. So e to the 0 power, that's 1. And to get c by itself, we would subtract 1.962 from both sides. So that would make c negative 1.962. So that means we could write velocity as, I'm going to call this 1.962, this one. And then c is a minus 1.962, e to the negative 5t. We plug c in, and now we have our velocity function. Once we have velocity, then we can integrate with respect to time, and that'll give us our position function. So when we integrate velocity, that gives us position. On the other side, when we integrate, let's do that on another page. We're going to be integrating 1.962 minus 1.962 e to the negative 5t. So since we have, let me check, make sure I copied that correctly. So since we have two terms, we're going to integrate these separately. So integrate the constant term with respect to time minus, let's put that constant out front. And then we're going to integrate e to the negative 5t with respect to time. So when we integrate a constant, we just pick up our variable. For the next term, to integrate, this is going to be e to the u du. So if u is negative 5t, then du is negative 5 dt. The derivative of the exponent is negative 5. So if we pick up a negative 5 here, we divide by negative 5 out front. Two negatives are going to make a positive. 1.962 divided by 5. 0.3924. And that's times e to the u, and then plus c. So when we integrate our right side, this is what we get. So our position function is going to be this. We need to know c, and what we know is that when we start our clock, we're saying that it has fallen 0 meters. The way we're measuring is we're measuring the distance it's traveled from the time we release it. So not the height above the ground, but how far it has fallen. So that means when we substitute a 0 in for t, our position should be 0. So 1.962 times 0 plus 0.3924 times e to the negative 5 times 0 plus c. So 0 times anything is 0. e to the 0 is 1, so we get 0.3924 there, plus c. So if we subtract that, we get c is negative 0.3924. So that makes our position function 1.962t plus 0.3924 e to the negative 5t, and then our constant is negative 0.3924. So that's our position function. And then if we need to know what its position is at any moment, then we can put that value in for t. Now, what all does it ask? When will the object strike the ground? When will the object strike the ground? So when it hits the ground, at the moment it hit the ground, it's fallen 3,000 meters. So we want to find out at what time will x be 3,000. Now, to solve this and get this exact, this would be quite challenging because notice we have a t here and we have a t in the exponent. But this is going to take several seconds for it to hit the ground. If it's falling 3,000 meters, this is going to take a little while. So notice if, for example, t is even 5 seconds. Then let's notice what is going to happen to this term, 0.3924. If we put 5 seconds in for t, then we're going to have e to the negative 25. Well, if we take e and raise it to the negative 25 power, that's exceptionally small. That's 1.39 times 10 to the negative 11. That's so small that that term has very little consequence at all. And then imagine that we're going to take that and still multiply that times 0.3924. So the order of magnitude of that is like 10 to the negative 12, which is really small. So to get a good approximation, we can say that by the time this hits the ground, this middle term is basically adding nothing. It's adding 0.000000 and then eventually some numbers. So we're just going to write that term off. And then we're going to solve using the rest of the equation. So we can add 0.3924 to both sides. So that gives us 3,000.3924 equals 1.962t. And then we can divide both sides by 1.962. So those cancel. So we get t to be 3,000.3924 divided by 1.962. 1529. And that's in seconds. Now that sounds really large. So I went into my math lab and I checked, and this is the correct answer. They do want us to go to 2 decimal places here. So 1529.25 seconds. Now, that seems like a really long time to fall, and it is a really long time to fall, but let's think how far we're falling. We're falling 3,000 meters. So it's fallen 3 kilometers. It's falling a long way. Also, B is a pretty large value. B being 50 newtons times second per meter. Then the air resistance is pushing on it quite quite hard. So the once it reaches terminal velocity, it's not going to be falling exceptionally fast. Now, we could find terminal velocity. That was not part of the question. But if we have the velocity function, which the velocity function was here, we could let time go to infinity. And if we let time go to infinity, we could find out what our terminal velocity is. If we let t go to infinity, then this term is going to go away, and we're left with our terminal velocity being 1.962 meters per second. So we could call that v terminal, about 1.962 meters per second. Well, it's not falling that fast the entire time, but if you think about if that's the fastest it goes and it's falling 3,000 meters, it's going to take it a while for it to get to the ground. So yeah, so that does make a little bit more sense on why our time is so large. Another problem we want to look at in this section, this is actually out of section 3.5, and this is what's known as an RC circuit. So in an RC circuit, you have a resistor and a capacitor. And we're going to have some voltage source. A lot of times that voltage source is a battery or something. Often we have a switch in here that as long as the switch is open, there's no voltage in the system, so there's no current flow. But then we close that switch and we immediately apply a certain voltage to the system. So voltage is just a potential, electrical potential in there. So when we close that switch, we have a current that runs through this circuit. It runs through the resistor, it runs through the capacitor, and then it makes this loop. And to begin with, the capacitor has no charge on it. There are different ways to make a capacitor, but they're basically parallel plates. And initially, before there's any electricity applied to the system, there are no charges on the plates. And then you run a current through it, and you start building up charge on the plates. And it essentially turns into kind of like a battery. You have a potential that's created between those two plates. And since these are in series, you have the same current that goes across the resistor as you have going across the capacitor. Now, one law of a circuit, there's a whole list of these. They're called Kirchhoff's laws. But one of Kirchhoff's laws says that when we sum the voltage in a system, the sum of the voltage should equal zero. What that basically means is, in our case, is that we have a voltage that's being applied from the battery, and then we're going to lose some voltage as we go across the resistor, and we're going to lose some voltage as we go across the capacitor, and that total is zero. So the applied voltage, and then take away the voltage that's used, and in that loop, our net voltage is zero because all of the electrical potential is being used. Now, our applied voltage, this is going to be a DC circuit, so it's going to be a constant voltage. Our resistance, the way you calculate voltage on a voltage on a resistor is equal to IR, the current times the resistance. Or if you know the voltage applied to it and you know the resistance of the resistor, you can find the current. So V over R equals I. So we're going to replace V, the voltage, with I times R. And then for the capacitor, the voltage on a capacitor is given by Q over C, where C is the capacitance, Q is the charge, or sometimes that's written 1 over C times Q. Now, current, that's the rate at which charge is changing, which charge is flowing. So that's the charge per unit time. So as the current is flowing across the capacitor, we're building up charge on that between those two plates. So over time, this charge is going to be changing. So the way we figure out what the charge is we take 1 over C and we integrate the current over time. Integrate the current over time. Notice current times time, I times dt, this is current, that's time. If you multiply that times time, the times would cancel and you'd be left with charge. So I over C, to get the charge, we integrate I dt. So over each little time increment, if we multiply the time increment times the current at that moment, that'll give us how much charge we've accumulated. And remember what an integral does, it accumulates, it adds together. The charge is not, or the current is not going to be a constant current. I say it's not going to be constant. It's going to be the same in both pieces. But when you first flip that switch, the current is going to go from 0 to, it's going to all of a sudden increase. So instantaneously, we are going to have a changing current that's going to be integrated over time. So we're wanting to eventually come up with a function that tells us what the current is at a given time. So Q, integrate current over time, that'll accumulate, that'll add up those charges. And when we do that times 1 over C, that'll give us the voltage drop across that capacitor, and that should equal 0. Our applied voltage, the voltage from the resistor, the voltage from the capacitor, that loop sums to 0. So let's plug some numbers in for our situation. Our applied voltage, when we flip our switch, it's going to immediately go straight to 6 volts. Our current is what we don't know. To begin with, our current is 0, and then we flip our switch, and then we have current flowing. The resistance of our resistor is 300 ohms. The capacitance is 10 to the negative 10 farads. So 1 over 10 to the negative 10 for C. And then that's times the integral of I dt, that equals 0. Notice this is actually not a differential equation. This equation has an integral instead of a derivative in it. So to convert this into a differential equation, let's take the derivative with respect to time. So when we take the derivative of a constant, we get 0. 300 is a coefficient, and when we take the derivative of I with respect to time, we get di dt. Pen froze there for a second. So di dt. If we have 10 to the negative 10 on bottom, that would go to the top as 10 to the positive 10. And if we take the derivative of an integral, the derivative and integral cancel, giving us I. So this is our differential equation involving I and di dt. We do this several ways. Notice if we multiply through by a negative, we would get 300 di over dt plus 10 to the 10th I equals 0. This is written in the format of a linear differential equation, or this one is one that we should be able to separate and integrate. We can move the I term to the right. Call this 300 di over dt equals negative 10 to the 10th times I. Divide both sides by 300. di over dt equals whatever this is, negative 10 to the 10th over 300 times I. And now we can separate and integrate. We can move I to the left, we can move dt to the right, and we can call this bi over I equals negative 10 to the 10th over 300 times dt. So divide both sides by I, multiply by dt, and we get this. So now integrate both sides. When we integrate the left side, that's natural log. Current is we're going to have a positive current. On the right side, we're integrating a constant, so negative 10 to the 10th over 300. We're integrating a constant, so we pick up our variable plus c. And then to get I, e to both sides. So e and natural log cancel, so I, current, as a function of time, is e to the negative 10 to the 10th over 300 times t plus c, or we can move that plus c out front as a capital C. So now we need to figure out c, and I slightly misspoke earlier. Before we flip the switch, before we apply voltage, it is true that our current is 0. But at the instant that voltage is applied, as soon as we close the switch and we apply 6 volts, then the current starts flowing through the resistor. And before we have a charge on the capacitor, when our charge is 0 to begin with, then our voltage across the capacitor is 0. 0 divided by whatever the capacitance is 0. So at the initial moment, then it's not that the current is 0. The current across the capacitor is 0, but the current is not 0. The voltage across there is. So the current that goes through here, that goes across the resistor, at the moment we start, when time is 0, all of our voltage is going across the resistor. The capacitor is not resisting that flow. So remember, V equals IR. There's no voltage on the capacitor. There's only voltage going across the resistor. So when t equals 0, the current at that time is just the applied voltage divided by the resistance. So to get C, then at t equals 0, the current is V over R. Put a 0 in for t. Well, if we put a 0 in for t, we get e to the 0, so that's 1. So that means C is V over R. So our current function is V over R times e to this power. So now let's look at what these things are. We have a negative. Before we move that 10 to the 10th to the top, it was 10 to the negative 10 on bottom, and that 10 to the negative 10 on bottom was the capacitance. That 300, that's the resistance, and then that's times time, so we could put T over here, or we could put T on top. So this is the general current function for the current in an RC circuit. V over R times e to the negative t over RC. Sometimes RC is replaced with the letter tau. Tau is the time constant for an RC circuit. We're not going to really worry too much about that for right now. So what is the question? That function is a function of current in our system. So our question says, if the capacitor is initially uncharged and the transmitting gate changes instantaneously from 0 to 6 volts, how long will it take for the voltage at the receiving gate to reach 5 volts? So when it says the receiving gate, if we go back and read this question, it says that the voltage source models the transmitting gate. So our battery or whatever our voltage source, that's our transmitting gate, and the capacitor is our receiving gate. So it wants to know when will our voltage on the capacitor, the receiving gate is the capacitor, when will that voltage be 5 volts? So find when the voltage on the capacitor is 5 volts. So how do we get voltage on the capacitor anyway? The voltage on the capacitor is 1 over C times Q, which Q is the integral of I dt. So the voltage on the capacitor is, we said Q over C, or 1 over C times Q, which Q is the integral of I dt. Well, we just came up with a function for I. This is our function I. So the voltage on the capacitor is 1 over C times the integral of V over R times e to the negative t over RC dt. So how are we going to do that? How are we going to integrate this? So V over R is a constant. So bring V over R out front. We already have C on bottom. That's times the integral of e to the negative t over RC dt. So this looks like this should integrate as e to the u du. So if u is negative t over RC, or we could bring the RC out front as negative 1 over RC times t, then du would be the derivative of that. This is a constant. The derivative of t is 1 dt. So that means we need to pick up a negative 1 over RC on the inside, and we need to multiply by negative RC over 1 on the outside. Notice the negative RC on top, negative RC on bottom cancels. So this would be e to the u, and that would be du. So the voltage on the capacitor, notice out front, the RCs would cancel. So that's going to give us negative V. When we integrate this, we're going to get, what does that give us? E to the u integrates into e to the u, where u is negative t over RC, plus, when we integrate, we pick up an arbitrary constant. So on the outside, we have our negative v. When we integrate e to the u du, we get e to the u, where u is negative t over RC plus k. Remember, we said that the voltage on the capacitor to begin with is 0. When we first flip the switch, there's no voltage on the capacitor. And then over time, that charge is building up, creating electrical potential or a voltage on the capacitor. So our voltage is 0 whenever we plug in a 0. Let's get rid of that parenthesis. Whenever we plug in a 0 for time. Plug a 0 in for time, and we get a 0 out front. So e to the 0, e to the 0 power is 1. So get negative V plus K, which if we solve for K, that means K equals V. So that means the voltage on the capacitor is minus V e to the negative T over RC plus V. Or we could rearrange that. Let's call that V minus V e to the negative T over RC. We could factor out of V, and that's 1 minus e to the negative T over RC. So this is the generic equation, the generic formula for our voltage across the capacitor. Now, we went in just for illustration, and we left our variables in there. We left R, we left C, but we could replace those for our specific problem. So for our specific problem, which we had put our numbers in earlier, and then we took them out just to show a general solution. But this V here, this is the applied voltage. So I believe we applied 6 volts e to the T is our variable. R is our resistance, which was 300, and our capacitance is 10 to the negative 10. So that's our function that tells us the voltage at time t on the capacitor. So we want to find out, when is the voltage on that gate going to be 5? When is the voltage on that gate going to be 5? So we just need to solve this equation. So we need to divide both sides by 6 first. So if we divide by 6, we'd have 5/6 on the left. Then let's subtract 1 from both sides. So the 1s are gone. So that's going to give us negative e to the negative t over 300 times 10 to the negative 10. On the other side, 5 over 6 minus 1, that would be negative 1/6. We could multiply both sides by a negative to make those positive. And then to get rid of the e, we can do natural log of both sides. So natural log of 1/6. If we take natural log of the right, the e goes away, leaving us negative t over 300 times 10 to the negative 10. So to get t, we're going to multiply both sides by 300. That'll make the 300s go away. Multiply both sides by 10 to the negative 10. That'll make 10 to the negative 10s go away. And we also need to multiply by a negative so that those negatives cancel. So that's going to leave us t on the right. On the other side, we're going to have negative 300 times 10 to the 10th, 10 raised to the negative 10, and then that's times the result of natural log of 1/6. So this is what we have out front. That's times natural log of 1/6, and we get 5.38, and this is times 10 to the negative 8, and that's in seconds. This is something that happens very, very quickly. So as soon as we turn that switch on, our voltage is going to ramp up across our capacitor. But it's not instantaneously. It does take a little bit of time, but not very much time at all.